Okay, we are live. Has anyone watched the YouTube lecture from yesterday? Please raise your hand if you have. Okay, so I'm going to assume that you have questions. In fact, I'm going to give a review on the assumption that you've all seen these two. It's actually two parts, part A and part B. Part A is about an hour, part B is about half an hour. I'm going to give a review assuming that you have seen that. Now, one thing I have to mention about the second one is that apparently someone pointed out that there were some audio problems. I was using extraordinarily expensive and high-quality audio equipment for those, and of course when I use the extraordinarily expensive high-quality audio equipment, the sound quality starts crackling, and there's a couple of minutes at the beginning of the lecture that's missing the audio, and there's actually one part where it suddenly gets very loud and starts crackling, and I didn't actually realize that at the time when I was recording it. But after about 2 minutes, it dies down, and you have, I think, pretty good audio, well, at least understandable audio for the rest of the talk, or the rest of the recording. So I apologize for that. I think in future I'll just use the cheap microphone that's on my laptop, which is the one that I've been using for the entire set of lectures that everybody's been commenting about how good the quality of the sound is. So we will just use the cheap laptop Steve Jobs microphone. Somehow it works. Okay, so this is lecture 11. So today's going to be a short lecture for reasons that I think I've mentioned. Raise your hand if you've received 6 announcements for the Stephen Boyd talk. Raise your hand if you've received 7 announcements for the Stephen Boyd talk. Raise your hand if you've received 8 announcements for the Stephen Boyd. 9? Anyone 9? 10? 11? I'm at 11. Anyone for 12? Anyone more than 12? Okay. Well, I think everybody knows that, and I think we got the message. In fact, we got the message so much that we're canceling. Well, we're not canceling because we've already done the first half of this lecture on YouTube, and so we're going to end this lecture early and walk over. It's just across the hall. We can actually literally from out our door see where this is, and so I can waste a lot of time making these jokes instead of having us walk down from Packard. And today, oh, by the way, what we're going to do today, this was really good timing because today we're going to talk about Shannon Games, which is an important and fun lecture. This is, again, our cumulative reading, as I've said before on YouTube, and I'm saying again now, this has not changed recently. This is the reading that you'll be required to do for the midterm. You do have a homework that's due tonight. You can't say that this class isn't a lot of work. I hope you're spending time on it. This is due tonight at 11:45, as usual. We're going to try to get this graded tomorrow, right? I will send you the solutions tonight. So basically, there's no lates accepted on this homework. Everybody do it, okay? I will send you the solutions at midnight, and then you will grade them by tomorrow, right? And so that way, if you have any questions, I will also open up some office hours tomorrow evening. Probably, actually, it'll be a little bit late, like maybe 9:30 or 10. But I'll create a Canvas discussion area at tomorrow evening if anyone wants to do last-minute discussion with me, and you can just join. And at the very least, we'll actually have a chance to debug this Canvas discussion thing. If it doesn't work, we'll just use Google Hangout or something. Question?
11.3 is the source coding or universal source coding. So, is it included?
Universal source coding? Yes, we definitely talked about that. We didn't necessarily talk about all ways that you could do universal source coding, but the concept of universal source coding we absolutely did talk about. In fact, the method of types gave us a universal source code. Remember? We're going to spend a little time on the midterm after I do this game thing, so let me just go through this. And we will spend a bit of time on the midterm. Okay. I'm going to monitor the clock, so I have, regardless of what happens. Okay, so midterm in class, I'm going to talk a little bit about it today. Stephen Boyd's lecture, it's in 105, it's across the hall. Yes, and we're doing this right now. We're meeting in this room. Okay. So here's a review. These are actual slides that we saw on YouTube. And the question was, Huffman is a symbol code, and we're putting one symbol at a time, and it's optimal in some sense, but is it optimal in all senses? And what exactly do we mean by optimal? And we have a source alphabet, and we need, if code word bits, we have to use an integral number of code word bits. We can't use fractional lengths. And so for d-adic distributions, there's all these nice advantages of such codes, and we could actually prove that we did at the end of last lecture bounds on, for example, how probable it is that a Shannon code length is going to be longer or shorter than any other instantaneous code. There are some examples of bad examples, like where we use many, many more bits using the Shannon lengths, and we need to use a long block length to get any benefit. The thing I wanted to mention again, just in case this isn't clear, is that we can use long blocks to get a better rate, but there are real practical problems with long blocks, because long blocks basically mean having essentially the ability to compute this probability table, which is exponentially large in n, which is the block length. In general, it's sort of hard to compute. It's hard to compute such a table. It's hard to compute, in some sense, the probabilities. I mean, unless you make an IID assumption, which you could do, and it would make it a little bit easier. But still, that wouldn't be in all real sources. If you're going to be using a long block, maybe you could get some additional benefit by trying to code for the entropy rate of the stochastic process rather than just the IID case. Okay, and we're going to talk about that. And the question, the real issue that's the problem is that this is just very, very high dimensional, and this becomes sort of a density estimation problem, or it's a problem in machine learning where you're trying to learn a probability distribution and you have samples of the data. And a good example are, for example, English sentences, or any language sentences, but English sentences. And you could potentially say anything, but there are still most things haven't been said. And I always say that this is something that you should try to do on search engines, which is either Google or Bing or whatever search engine you like. Try to find a very short phrase that has never ever been written down. And you can do that now, because certainly Google, they've indexed now every single, or an enormous number of printed books that have been written. It's going back historically before the web had ever existed, and so you can actually search for phrases. And the question is, how short of a phrase can you find that has never been written? Now, you could, obviously, if the word is in the language, then the word must have been written somewhere. But the question is, are there sequences of two words? And these are things that people might say. Like, for example, I'm going to demonstrate to you a nonsense sentence that's perfectly grammatical. And in an email or in a tweet, you might actually encounter such a sentence where two words which normally don't go together are together just because the speaker or the tweeter wants to give an example of something. And so what I did, I didn't actually try very hard. I didn't try to make this particularly short, but this phrase, I just checked, and dogs ate banks on the river, which doesn't make any semantic sense, but it certainly makes syntactic sense. It follows the rules of grammar. That sentence has never ever been written before. Very simple sentence. And so I challenge you all to the following quest: to go to Google or Bing and come back on, well, Thursday's a midterm. But come back and tell me. Maybe we could do this as via discussion. Why don't we do this? Let's do this through the discussion. Everybody post in the discussion area the shortest sentence they could find that's grammatical in English. I know everybody speaks like 15 languages here, but I don't speak 15 languages. But I think that if everybody could post the shortest possible sentence they can find that has never before been uttered, I think that would be interesting. And the point of this is that when you're trying to estimate, say, for example, a probability distribution of a language, like this guy, there are many, many things that do have some probability that will get a probability of 0 because they've never been seen. So this is a really, really hard problem. But if you could somehow solve this problem of density estimation, which there are solutions for, and in fact, when we talk about arithmetic coding, in some sense, we're going to talk a little bit about that, then you can actually extend the benefit of Huffman. So this is the Huffman bound. It's at most 1. It's sandwiched between the entropy and 1 plus the entropy. But if you use a block, it's still the same thing. It's the entropy now of the block, and then when you divide by n, then the 1 over n goes to 0. And so you can essentially, as long as you use a long block length, you can approach the entropy arbitrarily closely. But there's still several problems with this, and we're going to talk about this now. So one is that there are latencies introduced. We need to encode and then wait for the end of a block before we can do anything. Right? So for watching your Netflix movies or downloading a video or a PDF file even or something, you in some sense don't want to have to wait for the whole thing to reach you before you actually can start looking at it. And there's another problem which is a little bit more maybe insidious, which is that real sequential processes are not in fact stationary. Real sequential processes change. The probability distributions change from time to time. You look at, for example, economic forecasting. It's almost certainly not stationary. Every day, maybe the properties are slightly different. Every month, the properties are different. If you look at weather patterns, the properties of weather patterns today are not the same as they're going to be 5 years from now, or even 5 months from now. Things are not stationary. So what then we could essentially do is we could assume things are locally stationary. Like we could say, or let's define some window, some arbitrary window of some width, and say, okay, things are approximately stationary within that window. And that what that means is that within that window, things are not changing very much. And this is a problem already, because if the window is too narrow, your ability to estimate probability distributions with a small amount of data goes out the window. That no longer is good. Whereas if your window is too long, then the assumption of sort of locally stationary window goes out the window. I mean, the problem is that it's damned if you do and damned if you don't. If you have a short window, you're inaccurate. If you have a long window, inaccurate. And so people sort of, have a knob in the term, which is this window width, which is how much stuff, how wide of a window do you want to see in this stream of data when you're trying to sort of estimate the local heuristics. And so, you want this to be accurate because, we know now we can analyze this in terms of, for example, like Huffman. If the true distribution is p, and let's say p happens to be the local probability distribution from some stream of data, and if we estimate p prime, and p prime is different than p due either to the estimation inaccuracy caused by small window sizes, or it's inaccurate due to essentially it being an aggregate over multiple changing conditions, which sort of reflects a degree of smoothing which causes the inaccuracy. For either of those two reasons, this many number of bits per symbol will be k. The KL divergence is the bits per symbol that we're going to k in coding them. So we're going to be suboptimal, locally even. So instead what we could do is, we can sort of recompute the Huffman distribution each period. This is, I guess, the same thing. It's like, so what we're doing is like we have this distribution, we compute the Huffman distribution, and then somehow we encode with that distribution, but somehow we need to get that distribution over to the decoder as well. The decoder needs essentially to be communicated, and that distribution then, every once in a while, you need to somehow compress the distribution or encode the distribution itself, send that over, and that it also leads to an inefficiency. Now you're sending information over to the receiver, or I should say the decoder, the thing that does the decompression, about how to decompress, which is no good. So maybe there's some sort of adaptive Huffman scheme we could do that's a little bit smarter about this. And the question that we really want to get to, and this is getting into the notion of stream codes, is do we really want to do Huffman at all? Is Huffman really necessary? Or sort of have a probability distribution we encode, have a probability distribution encode. Is that really critical? And that's what we want to talk about now. So this is where the idea of stream codes come into play. Okay, but so this is what, what in order to understand stream codes, we're going to play a game. Okay, and I hope you will enjoy the game. This is a fun game. Everybody gets to participate. This is the only game we would play in this class. We normally don't get to play games in advanced graduate classes where nobody makes jokes and everybody's very serious all the time. But in this particular instance, we're actually going to play a game. So consider English. It's only because I speak English, not for any other reason. There's an enormous amount of redundancy in English sentences. Right? There's redundancy at the sentence level, at the word level, and at the character level, and maybe at the paragraph and at the paper level. Sometimes people publish the same paper in two conferences. That's a little bit redundant. Now, here's an example of redundancy. So this sentence, with more than 300 dead, most of the victims choked to, somebody complete that sentence. Death. Right? Let's see if we're right. Let's go to the next slide. We're right. So why do we even need to bother typing that? Why do we need, we didn't type anything, we just displayed it on the screen, but why did we need to waste the photons on, or I should say waste the lack of photons, with the blue photons? That doesn't make sense. Hope there are no physics people here. But why did we need to include the word death if we know what it is? Isn't that redundant? Isn't that a waste? What if it was instead? What if instead, whenever we wrote an email message or we wrote anything that was sort of so obviously and apparently inferable was just not included, and only in some sense sort of the essence, the core, the information contained within the message is what's actually written down on paper or on screen. So that's the idea of compression, right? Is that the redundancies are, you can predict. And what did we use to predict this? I mean, we actually had semantic knowledge of what the sentence is. This is a pretty dramatic sentence, right? It's 300 dead and choking to, this is something that's memorable and wow, this is terrible. And shouldn't be even smiling about this sentence, but here we are all smiling. At least I'm smiling, you guys aren't smiling. You guys are all teary-eyed and not very happy right now. And I apologize for bringing up such sad news, but in any event, I don't know where this is referred. This could be a sentence in any newspaper in any day, right? I mean, this is the world we live in. So anyway, let's play now. Right. So we didn't really need to see that last word. We could just predict it. Right. So Shannon, actually, believe it or not, this is something that Shannon realized, and he actually knew about this in his classic 1948 paper, and he actually tried to estimate the entropy of English text. And how could you imagine, and this is remarkable, this is truly remarkable. It's the 1940s, computers are the size of this room, the ones that have any processing power, and the ones that are the size of this room are probably, 100th as powerful as the kind of computer that you're going to get on your watch next year. And that's probably an understatement. So how can you imagine doing something as complicated as estimating the entropy of English text without any computers, without any ability to gather data? There's no Amazon Turk. There's no Google. Graduate students were wearing suits and ties, and all they did was write equations on pieces of paper. That's what those guys did at those days. Nobody had laptops. How can you do this? And Shannon somehow amazingly, derived a strategy called the Shannon Game to actually estimate the entropy of English text, and he was remarkably accurate. So first of all, let's just simplify the problem just to sort of introduce what a Shannon Game is. Let's pretend that we only have 27 symbols. Right? So obviously English has more, there's punctuation and everything, but we have 27 symbols, which are the capital letters, A through Z, and then a space. And here's the game. So given a letter history, we have some history of the letters, we ask a person to guess the following letter. And we count how many guesses it takes until they guess correctly. And we're going to play a Shannon game. So letters are given one at a time in sequence. And so what we're going to do now is we're going to do this. We're going to play a Shannon game. And I usually do this on a whiteboard. I'm going to try this on the iPad for the first time. To sort of facilitate our YouTube audience. Let's see if this works now. So the first letter obviously is, you have no idea what it's going to be saying. But and this is a little bit difficult because we're doing this in a group. But let's try having people guess. What's the first letter? E? So you guys got to guess.
S.
S.
R.
R. T. Ah, very good. Okay, so that's four guesses, right? What's the next letter?
E.
E.
H.
H. Oh, H. That's two guesses. Okay, let's write these numbers down. So 4, 2, and I'm going to do this thing. This is a little bit better. Oh, you can't do that.
Do you know how long the word is?
You're going to have to guess. Okay, so what's the next letter? We can do this faster. So
E.
E. Very good. That's one guess.
Space.
Space. One guess. Oh, no, that's wrong. Sorry. I missed that wrong. It's not space. But that's a good guess. Oh, so that's one guess. Space is one. 2 guesses.
E.
E. 1 guess.
Space.
Space. 1 guess. A. I. 2 guesses.
S.
Ah, very good. Space. 1 guess.
A.
A.
N.
N. Have you seen this before? Has anyone seen this before? No. So you've honestly not seen this before, because obviously if someone's read this sentence, this is actually this is not a sentence I made up, but I could have used a sentence that I made up. Would have had the same effect. But that's how many guesses? That's 2 guesses. Okay.
O.
Oh. 1 guess. Space. 1 guess.
O.
O.
P.
P. Don't be bashful. You gotta. So O, P, no. Keep going.
E again?
E. R. Wow, that's very good. Okay.
A.
Nope.
E.
E. 2 guesses.
A. D. S.
Keep going. There are other letters, you know. We haven't run out yet. Come on.
You want to be right though.
No, okay, good. Who's gonna get it? E.
N.
M.
M.
M. O.
P.
Now you guys are really gonna get that if you're just doing it by orders of letter. Alphabet order is not a good order to choose.
C.
C.
Q. Did I do R? Now we did
I.
R again. U. This is not answer the word. F.
G.
Oh, G.
Didn't anything yet.
J. K.
V.
What was that?
V.
V. Bravo. So how many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20, 21. 21 guesses
Wow.
on that one. Okay, next letter.
O.
Nope.
E.
E. Now we're back on track.
R. S. E. Space.
O.
R. O. P. F as in from?
N.
Oh, so it's 5 guesses. You're very good at guessing letters. Without you guys would still be guessing.
Space.
Space.
S. T. E.
A. 7.
No space.
No space. 1. I use context. There's no reverse on a bicycle. E. Not bad though.
C.
You thinking?
T.
T? M. 4. So you're guessing O, 1, T, 1, E, 1, R, 1, and then B.
O. P O.
Sorry?
Isn't it P O?
Motor. Is it motor? Am I spelling it wrong? Okay, it's still one guess. What's sorry.
C.
Ah.
Y. Cycle.
There you are. Okay. There's no reverse on a motorcycle. That's the sentence. Now, this sentence goes on, a friend of mine found out rather dramatically the other day, by the way, if you're wondering. So there's no reverse on a motorcycle. And here's another instance of it. So this is actually, this is what, I did this before in my class. This is what my class did last time. So they had, I think you guys had a little harder time on, actually I think I can copy this in. Let me just copy this. Just 1 second. I will copy this. This is the great thing about this whole iPad thing. Paste. Here's us. Now. Okay, so you did really good on the R, thanks to people over here. B was kind of difficult. I guess the hardest letter was B, 21. But overall, it's pretty good. But basically, the point was, as soon as you saw there's no reverse on A, you actually were able to, in order to reduce the number of guesses necessary. I mean, motorcycle. I mean, imagine just looking at the marginal frequencies. I mean, N is almost certainly not the most probable letter in the English language, right? But somehow in 4 guesses you knew it because you were thinking now semantically, well, what things don't have a reverse? And obviously, you're also making the assumption that, well, obviously it's not going to make a nonsensical sentence, like there's no reverse on a table or there's no reverse on a chair, which I could have said, it would have been grammatical, but you're making an assumption, you're using statistics. You're thinking, well, statistically, do I think that this professor is going to be conning me into sort of a semantically non-predictable sentence? No. Most of the time when you read a newspaper article or read a book or read all these different things, you're using context, you're using high-level knowledge and how there's semantics to do the prediction. Just how similarly you were able to predict the word death in the previous sentence. And so that allowed you to predict M very, very quickly. And then motorcycle, bicycle, that someone guessed B, and that was a very good guess, because there's also not a reverse on a bicycle. But the question is, we can tap into the human mind's probabilities by counting how many guesses it takes them to guess a letter in the context of a whole history of letters and sentences. Now you might think, okay, well great, that's counting, but how can I possibly estimate the entropy of English that way? Right. First of all, let's talk about what we're doing. In some sense, we're essentially producing a code for English. There's no reverse on a motorcycle. The sequence of guess numbers for the set of letters can, in some sense, be seen as a code. I mean, what we're doing is we're mapping from letters to numbers, right? But the mapping is not fixed. The mapping is very dynamic and it's changing. In fact, at each letter, it's a different mapping. But nonetheless, it's a code that should work. And often, the guesses are immediate. Look at what's the frequency of ones here? I mean, there's a lot. The most frequent symbol here is ones. And in fact, the number of ones is much more frequent than the most frequent letter. And in general, if you were to do this over a very, very long text, the number of ones would be much, much more frequent than the number of letter E's. So 1 is very frequent, 2 is going to be very frequent, 3 is going to be very frequent, whereas 21 is going to be very infrequent. There are going to be some letters that are hard to guess, but those aren't going to happen very often. And sometimes the same letter will be easy to guess, sometimes it will be hard to guess. And it doesn't matter, it's the letters change place in terms of their hardness based on what the current code is. So the things that are very predictable, things that have high probability, are highly ranked. They require fewer guesses. The things that require more guesses are low probability. Assuming, you guys said it exactly right when I said, please feel free to guess, and you said you want to be right. That's exactly what you want to do, right? Because you want to be right, so you're thinking about probabilistically, you're thinking about the context, you're thinking about all the things that you can bring to the table that will help you to predict that next letter. Which means that you're tapping into your model, your mental model of text. And the redundancy in English is how predictable it is. So if everything was the number 1, like when you watch Fox News, everything is the number 1. Right? Whereas if you watch something that's stimulating, intelligent, maybe there are lots of number 21s. Right? Maybe it's fewer ones. In some sense, this is very similar to, in some sense, a compression, right? You should never, before you read any paper, you should compress it. And if it compresses a lot, it's not worth reading because it's a waste it's not an efficient read. Right? Whereas if it doesn't compress, if it barely compresses, you can see, that's something I'm happy to spend some time with. Okay, so let's figure out how this corresponds to the entropy now. I want to be mindful of the time. Because you will soon see a lecture which is much more entertaining than mine. One of the things about Stephen Boyd is that he's just a fantastic lecturer. I think he combines comedic and technical depth into the same package, and I think that he's been an inspiration to, I think, a lot of people, including myself. But in any event, let's figure out how we can turn this into an entropic quantity. Because right now we just have numbers of guesses, we have integers. So let's say gt is the number of guesses of position t within the source string. So g is what you guys were providing me just now, g at each point t. And since g is an integer, and if we want to say, well, how many bits does it take to actually represent that integer? Let's take log of g. Log of g is the number of bits needed to represent an integer g. And we could steal it or something, but let's not worry about that right now. And we can estimate, in some sense, the entropy rate of this process in the following way. The entropy is approximately equal to 1 over n, the sum is equal to 1 to t of log of g. Now, how can that be? Right. Remember, the entropy rate is, we're defined, at least in the stationary stochastic process, we sort of define it in this particular way. This is sort of, again, sort of not worry too much yet about the whole stationariness bit. Let's assume that we're doing the window and we're doing some sort of things that are sort of locally stationary. The entropy rate of the stochastic process is the entropy of the tth random variable conditioned on the whole history, right? And it's based on this conditional probability, probability xt given the whole history. That's the probability. So if you had access to that probability distribution, so if something has a 1/10 probability, how many guesses do you think it's going to take until you guess it? About 10, right? If something has a 1/100th probability, it's going to take about 100 guesses before you get it. If something has a probability 1, it's going to take 0 guesses. And so therefore, the guess value of g of t, and remember, g of t is the number of guesses you made in the context of the whole history. So g of t really is, g of t depends on entire history. Before time t, right? So if we take the ratio of this probability, g of t is in some sense an estimate of the rate inverted 1 over the probability. And then if we plug this estimate into GT, suddenly it's 1 over n, some of you 1 over n of this probability, suddenly say, oh my god, that's the entropy. The guess is 1 over the probability. And so therefore, by looking at these guesses, I can say, whoops, oh, the punchline. What do we do here? We got way ahead of ourselves. I know what's happening. I will edit this part out. This is the right way we're getting to the punchline, and then I pressed the wrong button. There we are. So here we are. Does that look like the entropy rate of a stochastic process? Yes, it certainly does. And it turns out that we can get that from the number of guesses. Now, even at a time when you don't have computers, you don't have big tables, all you do is you have people who read a lot of books and people who understand the world and the context of everything. You could actually get these guesses. That's exactly what Shannon did. He had a bunch of students who were sitting around with pencils and paper and proving theorems, and he just said, can you guess this next letter? And he gave them these sheets, and he recorded how many guesses it took. That's something that students with pencils and papers can do, right, before they have computers and laptops. Right? So then, how would we compress this? A compression algorithm would transform the source string into the string of numbers, which is the numbers represent the number of guesses to get it. And we transform this, and then the frequency of 1s and 2s and 3s would be much higher. So it should be a very, very compressible source. I mean, we would have a very long string of 1s, right? And that's all we need to do is transmit that string of 1s. It's like it took 1 guess, and then took 1 guess, and took 1 guess, so on and so forth. However many guesses. So rather than sending, there's no reverse on a motorcycle to compress that string, we would send this string. Or if you guys were the decoder, the string of numbers that it took you to guess this. I should mention that in this particular case, maybe the first letter is a given. Like if I gave you T and you guessed the next one. What I did is I asked you to guess the first letter. So that's okay too. You just essentially use the marginal probabilities, and E was I think the first guess, and that was the right thing to do because that's the most probable one, not knowing anything. It's the one if you don't know anything. And so this string of numbers should compress very, very well. Then how do we decode? Well, what if I did the following? What if I could somehow time travel back to when I asked you about this guessing game as well? And I started you guessing letters, but as soon as you got to the 4th guess, I would stop and say, there's letter. Then I would ask you to code again, start guessing, and each time you get to the number of guesses in the integer count that I've now stored, I would stop you from guessing and then tell you to go on to the next letter. So as long as in some sense I can time travel, or equivalently I have an identical twin who's located at the decoding side of things, I can essentially do decompression. I literally just ask that entity, whether it's a body of people or a decoding algorithm, to just keep guessing letters until I've guessed that many guesses, and then I stop them at that many number of guesses. And that becomes the decoded character, and then I move on to the next character. And in such case, we'll recover the source message. So all I need, like if it's a probability distribution or a guessing engine that I can duplicate. And the guessing engine can be adaptive, because every time, if I've got the count, the person does, is it T? No. Is it R? No. Is it S? No. Is it E? Yes. Boing. And then it becomes part of the history, and then I can update my conditional distribution, because now I know what the letter is. And that thing, as long as that guy adapts in the same way as the encoding distribution adapts, then I can completely losslessly reconstruct the message. Now, you could potentially, I talked a little bit about adaptation. I mean, one thing you could do is actually have a big, very, very large table of all possible probabilities for all histories. That's not what we're going to do, because then we get into the same kind of estimation problem in large table size that we had with the block coding. But it turns out that there's going to be adaptive methods of probability estimation, possibly very similar to what humans do, where we estimate only the conditional distribution, and as soon as we guess right, we update our conditioning context in a way that somehow doesn't expand exponentially with the history, even though the history is growing. That's sort of, and obviously the only way to do that is to do, instead of p of x of t given x of 1 through x of t minus 1, we're going to say this is approximately equal to p of x of t given some statistic on x1 through x of t minus 1. And as soon as we guess right at time t, that guess becomes part of the input to the statistic. And as long as we can update the statistic, we don't actually need to keep this whole context. The statistic might be how many of each character there is. So there might be something. The point is, it's still something that can depend arbitrarily on the past, but we don't have an exponential for it. So maybe that's what humans do. So in any event, that's what Shannon did in the late 1940s, early 1950s. And that's the basis for the idea of arithmetic coding, which is what we're going to talk about. Obviously not today, but I just want to well, actually, we have a little bit of time. So has anyone heard of arithmetic coding before? All right, so that's something that's used a lot for document image compression, like deja GNU, or deja vu, whatever it's called. It's a document compression standard that was developed by AT&T in the 1990s and late 90s, and it was actually at the time extraordinarily good. It compressed documents down and had very, very high quality. But at the same time, PDF was a competing standard, and PDF, as you know, because I'm asking everybody to submit their homeworks in PDF format, is the dominant standard, thanks to this class, of course. But deja vu is still around, and you can actually still buy compressors, and they use arithmetic coding. In fact, to be honest, as a result of this, more recent versions of PDF have instances of arithmetic coding in them. And you need a probabilistic model. And so the probabilistic model, a very simple one that wouldn't work very well would be the IID assumption. But maybe a better one would be first order Markov assumption. And we're going to talk, when we actually introduce arithmetic coding and the core concepts, we're going to talk about some more sophisticated models, higher order Markov models. Okay, so let's see now what time it is. Let me just pause for questions before we move on to this next topic. Any questions about what we've just done? So does everyone see the potential of this idea? The idea again is, if we're sending, this can be in some sense like a stream code, and arithmetic coding is a form of a stream code. As soon as we receive a number, we can just run this guessing engine and have it guess a certain number of times until we stop it at that integer, g of t. And then we've got a character. And we've got a little bit more of the signal. And then we update the history, and we do it again. And so it's a stream code, right? We don't have to wait for the end of the signal. We don't have to wait for the end of the stream before we can start decoding. There's no latency, or there's no appreciable latency. If we can somehow do that in an algorithmic way. Obviously, like you guys probably are not for hire as a decoding compression engine, you collectively as a class, probably, or maybe you should. Maybe you can go collectively, like after class, you can say, hey, let's go to Amazon Turk, and we're going to offer to compress and decompress people's signals for like 5 cents per message or something. But I don't think you want to do that. Are there any questions? Yep. Okay, so you prefer to talk about the midterm. So now I want to go to a thing, and I'm not able to get there. Okay, so midterm, like I said, will cover everything up until chapter 5. So obviously we didn't cover arithmetic coding, so we're not going to include that. but it might cover the Shannon Elias coding, the stuff that occurred a little bit yesterday on the YouTube video. So I suggest everybody watch the YouTube video. Again, apologies for the sound, but I think the stuff that was 2 minutes was just at the very beginning, and there wasn't really anything that deep. You can get it from the slides, which are also on the web page. It will. I don't think it's going to be super hard. I mean, it's going to try to be diverse. In other words, it's going to attempt to try to cover all of the topics that we've covered. I mean, and sort of act as a sanity check. Because after arithmetic coding, we're going to start talking about channel coding. And channel coding is in some sense dual to what we've been doing. It's dual to compression. It's like what we've been doing is compressing an information source down to the entropy. And the entropy is sort of the fundamental lower limit. It's a measure of it's sort of a measure of the information that exists in a source. Channel coding says that there's sort of a fundamental maximal throughput through a channel that we can communicate with vanishingly small probability of error with increasing block length. But it's like I said, you're trying to do it's a maximization problem as opposed to compression, which is a minimization problem. And there's a notion of rate. When you're doing compression, you want the rate to be small. When you're doing communication, you want the rate to be large. And so that's how, in some sense, it's dual. There's lots of ways. We'll talk about that next week. But are there any questions about the midterm?
We're expecting something similar to that.
No, it'll be. I mean, some of the homework problems are more involved. I mean, this is obviously something that I want you to be able to do in an hour and 50 minutes. So I don't think it's going to, I mean, some of the homework problems involve some algebra. I mean, everybody has to do algebra occasionally, but I usually don't like to ask, long algebraic derivations in class. I think there's a time for that. Everybody needs to do that, but that's best done at home late at night by candlelight or something. I think when you're in the class in the midterm by fluorescent light, you should just be asked conceptual questions. Other questions? Do you have any questions for our TA? Would you like to ask him any questions? If it's a hard question, I always just let him answer. Right? No questions about the midterm?
Do you have any questions?
Wouldn't it be better to ask me what the entropy of the midterm is? The entropy of the midterm will be about 6 or 7 bits, maybe. That's the fundamental measure of how many problems. Sorry, what? How many problems? That's what I was saying. Like, I think you should that doesn't matter, right? I mean, it really depends how much information is in the midterm, not how many questions. If there were 100 questions and they were simple yes or no questions, would that tell you anything?
Well, there'd be a lot of redundancy.
Not necessarily. It just could be, I mean, there's sort of fundamental information. If there's 100 questions, lots of redundancy, very easy. So anywhere between, I don't know. I haven't finished writing. No, probably to be, I mean, if you really want an answer, it's probably going to be about 10, roughly. I'll actually, what I should do, I will post a midterm from last year's. How about that? So I will put it on the Canvas page. That's where it'll go. And if I don't do it tonight, someone send me a reminder, okay? It'll be there by tomorrow. Okay, well, I will see you on Thursday, and don't forget about the talk across the hall, and talk to you soon.